Welcome to the online video lecture series for intermediate algebra at Wayland Baptist University. My name is Dr. Scott Franklin, and I will be conducting these lectures. This is Chapter 5, where we begin talking about the next level of functions. We're going to increase the complexity just a little bit to move on from linear equations to talk about polynomial equations, and we will introduce and define what polynomials are, how we do certain operations with them, and eventually get to the point that we can solve equations that involve polynomial functions. This is section 5.1, Introduction to Polynomials and Polynomial Functions. In this section, we're going to be talking about how we use the vocabulary of polynomials, how we evaluate polynomial functions. We're going to talk about end behavior, what happens on the ends of the graph. So really we're going to be talking about the graphs of polynomial functions when we get to this section, and also talking about how to add and subtract polynomials. Now what we're going to do as we go through and discuss these new types of functions is we're going to first define them so we fully understand what they are, what's new about these functions as opposed to functions we've looked at before. And then we're going to go through the whole procedure of adding, subtracting. In later sections we'll multiply, we'll divide, and then we'll talk about something called factoring, because factoring is necessary when we finally get to that culmination of the chapter, that most important aspect, and that's solving equations, finding the unknown or missing piece in a polynomial equation. So once we learn all about how to add, subtract, multiply, divide, we're then going to factor, then we're going to solve equations, and of course we're going to do word problems all throughout and along the way. So let's get started by defining what a polynomial is and some of the important terminology that we use with polynomials. To begin with, let's start by answering the question, what is a polynomial? Strictly speaking, a polynomial is a finite sum of terms with whole number exponents. In other words, a polynomial is an expression such that no variable appears in the denominator and there are no roots, or equivalently, there are no fractions in the exponents. There are fractional exponents. Okay, so what does that look like? Well, it's when you have a series of things added together, but the only exponents that you see are whole numbers, and there are no variables in the denominator and no roots. So things like x squared plus 3x minus 4 would be an example of a polynomial. Okay, whole number exponents. Okay, finite sum of terms. All I mean by finite is that I don't have something at the end that goes dot 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 dot, that it just doesn't keep going. No, it has to actually have a total number of terms that you can count of. Like, for example, this one has 3 terms, whereas what I mean by terms, and we'll define this explicitly later, is what are separated by addition and subtraction. So this has 3 terms. Okay, you can also have longer polynomials, say higher powers than just x squared, so 49x cubed plus 806x squared plus 3776x plus 2503. I pulled this out of the textbook. It's a polynomial that represents a particular model, but it's still polynomial because you have whole number exponents, no variables in the denominator, no roots or fractional exponents. But you can also have polynomials in multiple variables. So you could have something like 7x squared y cubed minus 17x to the 4th y squared plus, say, xy. There's an example of a polynomial in 2 variables. Now generally, although this is not a hard and fast rule, but generally we write terms in order of descending powers. So when we are finally done with a polynomial problem, the last form the answer takes will usually be in some descending order. Notice how I started with the square, then had the first power, and then had no x at all. This had a cubed, squared, first power, so it's 3, 2, 1, and then no power, right? Meaning x to the 0 or just no x at all. Okay, this is generally called standard form. The terms, and I've already mentioned this above, The terms of a polynomial are the parts separated by addition. And why I don't say addition and subtraction is because, remember, subtraction is just addition in disguise. But if I were to say, look at that first one, x squared plus 3x and a minus 4, the terms are x squared, that's the first term, 3x is the next term, and negative 4, where we include the sign with it, the negative 4 is the last term. So there are 3 terms in that. Now for each term we have something called the degree that will describe a property that that term has. The degree is the sum of the exponents of its variables. So say for example I was looking at this term here, the 7x squared y cubed. That's a term out of this last polynomial in my examples above. The degree of that term would be 5 because you add the exponents of the variables. So that would be a degree 5 term. Now we've talked about the degree for a term. If we talk about the degree of a polynomial, right, which a polynomial will generally have several terms in it, what we mean by that is the degree of the term with the, and the blank is actually supposed to be this word, with the highest degree. Okay, the degree for a polynomial is the degree of the term with the highest degree. So say I had 7x squared y cubed minus 17x to the 4th y squared plus xy. The question is, what's the degree of that polynomial? Well, what you do is you check the degree of each term. The degree of this one is 6, right? Sorry, 5. The degree of the first one is 5. The degree of the second one is 6 because it's 4 plus 2. And the degree of the last one would be 2. Remember, if there's no exponents, it's understood to be 1. So that's 1 plus 1 gives me 2. So the degree is not the sum of these, but the highest one. Okay? So 6 is the highest degree. So the degree of that polynomial is 6. Now we always call the term with the highest degree, it's given the name the leading term. So in our case, the leading term would be right here. Okay? Now the number in front of each term, right, like the 7, the negative 17, and the positive 1, is called the term's coefficient. I will talk about coefficients, and I may even use that term or that nomenclature somewhere along in the course, but now I'm explicitly defining it for you. Coefficient is the number that is in front of the variables in each term. Okay? And in the case that we're talking about the leading term, we sometimes refer to the coefficient of the leading term as the leading coefficient. Okay? So above, the coefficients would be 7, negative 17, and 1. And the leading coefficient would be negative 17. Okay? So those are some of the terminology words, the words that we use to describe different aspects of a polynomial. Now we also give names to different types of polynomials. Although I don't use this all that frequently, you'll hear me use these terms along the way. Polynomial that has one term is called a monomial. So a monomial would be just a single term polynomial, like 7x squared y cubed. That's a monomial. Let's say put 4x. That's a monomial. 3yz. Those are all 3 monomials because they have only one term. If a polynomial has 2 terms, we call it a binomial. So something like, I don't know, x plus 4. Maybe something like 3x squared minus 9y squared. That's a binomial. And if we have 3 terms, We'll call it a trinomial. We could keep going, but I think generally we stop. Nobody talks about tetranomials or quadrinomials. Maybe not quintinomials. We don't go that far. We stop at trinomials. Anything more than that, we just always call them polynomials. In fact, all of these, even a monomial, binomial, trinomial, are also polynomials. They're just given a special name sometimes when it's necessary to describe the number of terms that we're talking about. So something like x squared plus 3x minus 4 is a trinomial. A squared minus 2ab plus b squared is an example of a trinomial. Let's put our terminology to use a little bit. In these following examples, we're asked to find the coefficient of each term, the degree of each term, the leading term, and the leading coefficient for the following polynomials. So to begin with, let's identify the coefficients of this first polynomial. Okay, I'm just going to list them, comma separated. Okay, so the coefficient of the first term would be 2. The coefficient of the second term, remember to include the sign, it's negative 9. The coefficient of the third term, when there's no number in front, remember it's understood to be a 1, so that would be a negative 1. And the coefficient of the last term, even though there's no variable, so the number itself is the coefficient, is going to be 5. Okay, what about the degrees? What are the degrees of each of these terms? Okay, what's the degree of the first term? Right, remember you only check the variables. You add their exponents. Now in this case we only have one variable, so it's going to be the exponent of that variable. So the first degree term is 3. The degree of the second term is 4 from here. The degree of the next term is the power of the x, which is also understood to be a 1. And when there is no variable, the degree is 0. And the reason for that is you can think of, we'll go off to the side here and make a note of this, x to the 0, right? Remember from our previous sections, remember the 0 exponent rule said that when you have a 0 power, it's understood to be 1. Okay, so this would be the same as like 5 times 1, right? Or 5 times x to the 0, thus we get a 0 degree. All right, now I don't ask for it here, but let's go ahead and include this. What is the degree of the polynomial itself? What's the degree of this whole polynomial? It's going to be a 4th degree because the highest is 4, so it's a 4th degree polynomial. It's important to note. And you can also identify that. I mean, it's important to know because that's where you're going to get the leading coefficient from. The leading coefficient will be from the term with the highest degree. So that's going to be negative 9. Well, I should say, let me do this. Let's do the leading term first. And of course, the leading coefficient would be the coefficient of that term. I think that's the order I asked for here. So leading term is 9x to the 4th, negative 9x to the 4th. And the leading coefficient, abbreviated COEF, is negative 9. On example B, we're given 12x to the 4th y minus 5x cubed y to the 7th minus x squared plus 4. And again, we're going to find the coefficients, the degrees of the terms, what the leading term is, and what the leading coefficient is. So the coefficients, in this case, would be 12, negative 5, negative 1, and 4. The degrees of each term, right, is going to be the sum of the exponents. So in this case, 4 plus 1 gives me a 5 for the first term. Gives me a 10, right? 3 plus 7 is 10 for the second term. The third term has a degree of 2, and the last term has no variable, so it has a degree of 0. The leading term would be the one with the highest power, right? And that highest power is also telling us what the degree of the polynomial is. That's a 10th degree polynomial. So the leading term is the one whose degree is 10, which is this term right here. So negative 5x to the 3rd, y to the 7th, which has a leading coefficient of negative 5. Same thing on this one, so let's put down what we're asked to find. The coefficients will be 3, 4, -1, 4, and -5. Right? 3 here, 4 here, -1, +4, -5. The degrees of each term we can find by adding the exponents. So 4, and then 4 plus 4 is 8. 3 plus 1 is 4. There's just a 2 here and 0. So it's an 8th degree polynomial from here, which means this is the leading term. So 4x to the 4th, y to the 4th. By the way, it's just coincidence that the three problems I gave here had all the leading terms in the second place. They can be any place at all. Okay, and so the leading coefficient is 4. All right. That's the terminology section of this section. Now let's talk about polynomial functions. So a polynomial function, as opposed to just a polynomial, is going to be something that is in fact a function, meaning that we're going to use function notation like we have seen earlier in this course. It's a function whose rule or formula is a polynomial. So whenever I have f of x is equal to some polynomial in x, that's going to be a polynomial function. So all we're really being asked to do at this point is make sure that we can still use function notation when the formulas happen to be polynomials, which is nothing really new to us. In this case, we are given the following polynomial function. F of x is equal to negative 2,212 x squared plus 57,575x plus 107,896. This polynomial function models the cumulative number of deaths from AIDS in the United States, f of x years after 1990. We want to use the function to answer the question. What do we mean by f of 8? So find the value of f of 8 and interpret what that means. Okay? So first of all, f of 8, remember f of 8 just means plug in 8 for x. So negative 2,212. Replace the x with 8 plus 57,575. Replace the x with 8 plus 107,896. All right, now going to my calculator, I see that, of course, 8 squared, I don't need my calculator for that. I'll use my calculator on the next step, but 8 squared is 64 plus 57,575 times 8 plus 107,896. Now if I take in my calculator negative 2,212 times 64, I get 141,568, and that's negative, plus 57,575 times 8 is 460,600, and we still got the 107,896. Now add those three numbers up, I end up with 426,928. Okay? So that means that according to this model, the model given by this function right here, 426,928 deaths from AIDS in the U.S. occurred, if I can write occurred, I apologize for spelling here. Let's try that again. Occurred, O-C-C-U-R-R-E-D, in, what, 8 years after 1990, so in 1998. That's the interpretation of this value. We're not going to talk too much about the graphs of polynomials in this section, but there are a couple of things that I do want to point out about the graphs of these types of functions. And then we'll look at more detail of graphs of specific polynomial functions like quadratic functions later on, not in this course, but whenever you take, if you take college algebra, for from Wayland, we will cover quadratic functions in that course and look at the shapes of those graphs and learn a lot of the details that go into those shapes. But let me point out at least a couple of things that are true about all polynomial functions if you were to graph them. And if I were to ask you to graph them, if they showed up in your homework, all you're going to use to graph is the value table method, right? You're going to pick different values for x, plug it in, find the y's, and then plot those points and draw a curve through them. But here's what you should note. Polynomials are smooth. There are no sharp corners in a polynomial graph. Okay? The other thing is there are no breaks. It's continuous, right? It doesn't ever jump. So you can see in these two examples, these are smooth, and what will happen, actually, I don't state this in one of the numbers up here, but they will extend on forever. Like these have arrowheads at the end, meaning they go on forever. Okay? There's no breaks, and there's no sharp corners. So these are not polynomial functions over here. There is one other thing I want to tell you about polynomials, and it's kind of related to what I mentioned before, where you see that they go off forever at the end. The curves continue on at the end of these graphs, but there's something about what happens at the ends that we can tell by just looking at the polynomial. We don't have to graph it. Okay? There are four possibilities. Either the curve goes down at the left and up at the right. It either goes up at the left and down at the right, or it's both up at each ends, or it's both down at each end. Okay? Those are the only four possibilities. It won't bounce back and forth forever. Eventually, it'll always go down when you go far enough to the left. It'll always go up, or one of these other three possibilities. So you got four different possibilities. And the way that you tell what's going to happen at the ends is by looking at the leading coefficient, okay, and the degree of the polynomial. Okay? You check the degree, you check the leading coefficient. Okay? Now here's the four cases that we have. We have odd degree, and we have positive coefficient. We have odd degree, and we have negative coefficient. If we have an even degree, we can have positive coefficient for the leading term, and if we have an even degree, we have a negative coefficient. Okay? Now if it's odd, they go opposite directions. Okay? And the positive tells you what happens at the right inside. Okay? So, if it's an odd degree polynomial and the leading coefficient is positive, that means as you go to the left it falls or it goes down. As you go to the right it goes up. Okay? If you have an odd degree and a negative coefficient for the leading term, then it's going to rise to the left and fall to the right. For an even degree polynomial, if the leading coefficient is positive, then they rise in both directions. Okay? And if the leading coefficient is negative for an even degree polynomial, they will fall or go in the negative direction on both ends. So let's use the leading coefficient test to interpret a problem that has a polynomial function. So the common cold is caused by something called the rhinovirus. After X days of invasion by viral particles, we can model the number of viral particles in our bodies by this function right here. And what that function tells us is that the output is in billions, and X is the number of days of the infection. Okay, now we're going to use the leading coefficient test to determine the group's end behavior to the right. Okay, what happens as we go on to the right? Okay, so first of all, what is the leading term in this? Okay, we've got the x squared term, the x cubed term, and the 0 degree term of the 5. Right? The leading term is going to be this one because it has the highest degree, 3x to the third. Okay? The leading coefficient then is 3. So according to this leading coefficient test, we have a degree 3 polynomial from here with a leading coefficient of 3. So that would be odd degree with a positive leading coefficient, which means it rises to the right. Okay? So what that says is, according to the model, the number of particles would continue to grow over time. The number of particles continues to grow over time. Now let's talk about how we add polynomials. Now that we've got these new types of functions that we're going to be working with, we know what they are, we know what polynomials are, we know how to evaluate them functions, we even know a little bit about their graphs. But what we're ready to do now is to do our arithmetic operations with these polynomial functions. Okay, so since polynomial functions can represent any type of real quantity, like above they were representing the number of different viral particles, right? Then in different scenarios where the functions are modeling these real world things, it's not uncommon for us to see those kind of things being added together or multiplied together or subtracted, all those kind of things. So we're going to talk about how we do those operations with functions which are polynomials. Now the easiest type of operation to do with polynomials is to add them together. In fact, you already know how to do this. We've done this type of operation before. When you add polynomials together, you're just going to collect like terms. That's it. That's all you got to do is collect like terms. We've collected like terms in linear equations, but now we're going to do it when we have exponents. All we got to remember is like terms are the same variables with the same exponents. Okay, so here's a polynomial, negative 6x cubed plus 5x squared plus 4, and we're adding it to the polynomial 2x cubed plus 7x squared minus 10. Okay, so first thing I want to do is, since there are parentheses, is I check inside the parentheses to see if I can simplify. And there's nothing inside the parentheses that I can do. So I'm going to get rid of the parentheses, right? It's understood to be just a 1 out in front. Multiplying by 1 doesn't change anything, so in this case I can just drop the parentheses. I'll have negative 6x cubed plus 5x squared plus 4. Okay, same thing here. Plus 1 times this thing is going to be just itself, so plus 2x cubed plus 7x squared minus 10. I was able to just drop the parentheses in an addition problem. Now I collect like terms. Now what are like terms? They're the same variable, same exponent. So this has an x cubed in it. The next one that has an x cubed is this one. So I'm going to add them together by adding their coefficients. So I take negative 6 plus 2 and I get negative 4 and keep the term the same. Okay, and I will have combined those. 5x squared, the next like term did is going to be the 7x squared. So 5x squared plus 7x squared is plus 12x squared. So I've taken care of those. Now I've got 4 and minus 10. I can combine those to get a minus 6. That is completely simplified because I cannot combine any more like terms. So I've added those two polynomials together to get one simpler polynomial. And what's interesting to note, in case you weren't aware of this, if I were to plug a number in for x up here and work it out, I would get the same thing as if I plugged it into this equation, or this function, or this formula. Right? By simplifying, we now have a simpler formula to work with, which always gives the same output as the original. That's what we're trying to do, is get to a simpler version of the formula. And adding these polynomials by collecting like terms does that for us. And that's it. Let's do one more, same way. We can drop the parentheses because there's just a positive 1 out in front of each one of them. So I had negative 7x cubed plus 6x squared minus 11x plus 13 plus 19x cubed minus 11x squared plus 7x minus 17. And then collect our like terms. So our x cubes will go together. I'll have negative 7x cubed plus 19x cubed gives me a 12x cubed. Combine my x squares. 6 minus 11 is minus 5 x squared. Minus 11x plus 7x is minus 4x. And 13 minus 17 is minus 4. And there you go. That's all you got to do to add polynomials together. Alright, so we've added. Let's subtract. Now what's the difference between addition and subtraction? It's just this sign right there is now negative, right? The only difference now is the middle sign is a minus sign. Now what you got to note here is this minus is subtracting the whole polynomial. So this is like a minus 1 sitting in front here. And just like I mentioned before, but it didn't really do anything, I had to multiply out this 1, positive 1 times this whole polynomial. Positive 1 times something doesn't change it at all. So it just looks like I dropped the parentheses up here. But down here, if I want to subtract polynomials, the only thing I got to do different is remember to always, and use the right grammar, but always distribute, sorry about the typo, fix that on the next edition, always distribute the negative. Now I want you to take your pen and I want you to circle that after you've corrected it. I want you to put some exclamation points, some stars, okay? I've got my different colors here, so I'm going to highlight this as being very, very important. Okay? Why is that so important? Because that's the mistake that is one of the most common mistakes throughout latter portions of algebra, is forgetting to distribute that negative sign whenever you subtract. In my traditional classes, I will often make students recite this over and over. We shout it at the top of our lungs so the entire building can hear that when subtracting, always, always, always distribute the negative. And then when you're done with that, well, it's just like the same old problem. You just collect like terms. Collect like terms. Okay, so let's do this example here. We got a subtraction. Let me get rid of the junk that I've written on there. Okay, 5x to the fourth y squared plus 6x cubed y minus 7y minus the quantity 3x to the fourth y squared minus 5x cubed y minus 6y plus 8x. So to begin with, I can distribute the 1 that's in front of the first parentheses, which does not change them at all. So I have 5x to the fourth y squared plus 6y cubed, so x cubed y minus 7y. So it's the same as it was before. Now distribute the minus sign. Means apply a negative to every term inside. Minus 3x to the fourth y squared looks like this. Right? Minus times a 3 becomes a minus 3. Minus times a minus 5 is a plus 5x cubed y. Notice how if I were to drop the parentheses, I've already got the sign wrong. Here, I've got to remember to distribute it. Minus times a minus is plus 6y. And minus times 8x is minus 8x. Now let's collect like terms. So I have x to the fourth y squared. The other term that has that would be this one. 5 minus 3 is 2x to the fourth y squared. I have an x cubed y and an x cubed y. 6 plus 5 is 11, positive, so plus 11x cubed y. Minus 7y plus 6y. Minus 7 plus 6 is minus 1, so minus 1y. Right, and then I've got just the minus 8x sitting there by itself. So that is completely simplified. We've subtracted those two polynomials. And that's the end of section 5.1. We've added, subtracted. We're going to come back and multiply in the next section.